This webinar will look at how Maple can be used to enhance a first course in differential calculus. Part of the enhancement is the use of syntax-free techniques. So the calculus syllabus immediately is taught, not the tool. And part of the enhancement is the illustration of resequencing of skills and concepts. That's a phrase that comes up in the literature, and it means that concepts are addressed first, because the typical calculus text drills students first in manipulative skills so that they can be used to juggle the concepts. Well, with Maple being used to juggle the concepts, you can make the concept clear first. Then you can use Maple to illustrate the stepwise skills needed. And all of that comes before this, requiring the student to master requisite calculations. And I've seen this work in my own courses at Rose-Hulman, and I think this evolved for me as the optimal usage of Maple in the classroom. So in a differential calculus course, one of the first things that might arise is the application of the definition of the derivative to various functions. So here's one where I'm going to apply the definition derivative to polynomial. Now, I'm envisioning here that all of that stuff about the tangent line becoming a secant line becoming a tangent line, and all of that stuff has already been done graphically and numerically, whatever. And now you want to actually look at the analytical manipulations. So I want to define this function. So I will select it. I'll hold down the control key and drag it down to where I want to work on it. And you'll see this phrase control drag. That's equivalent to a copy paste. It's not a Maple thing, it's a Windows thing. I'm in Windows. But it can be done in other operating systems because I've checked that. Now I'm going to go to the context panel and select assign function, and that does all of the background work of defining that function. Now I want to implement the definition, which is the limit of the difference quotient. Now I could just drag this thing over, but I want to show you how it's created. So I have this limit operator in my favorites palette. Now I'll just show you how you put stuff in your favorites palette. So here's a calculus palette, and that limit operator is right there. So you would right click on it and you would select add to favorites. That's how I populated my favorites palette, and I'm going to just use my favorites palette here. So there's the limit operator, and you type H, use the tab key, goes to 0, and now I want to put in the difference quotient. If I type H and hit the slash key twice, H will go down at the denominator, and I type f of x plus h minus f of x. Oh, I made this one a capital. It's lowercase. Okay, I want to evaluate this thing. So if I go here to the context panel, I see this evaluate and display in line. In other words, that limit will be evaluated, and then Maple will put in an equal sign, and it will put the evaluation in line with the limit operator. There's a keyboard equivalent that I'm going to frequently use, and the one I use is Control equal. My fingers are trained to do Control equal, but I believe Alt Enter is another equivalent. So you can go to the panel, or you can use Control equal, and I'm going to use Control equal. And so you get 9x squared minus 11. Now what does 9x squared minus 11 mean? If we type f of x and hit the enter key, we get echoes the rule. If I go to the context panel, I find differentiate with respect to x. And so if I perform this operation called differentiate with respect to x, I get 9x squared minus 11. So this limit of the difference quotient is equivalent to differentiate. Okay, now let's look at this from first principles. We want to examine that difference quotient. What is f of x plus h minus f of x look like? Now, I'll eventually get this right. F of x plus h minus f of x. Okay, I'm going to hit the enter key, and I look at this expression, and I say, I have something to expand. So, context panel, now you can use expand or you could use simplify, but you want to multiply this thing out. And you look and you see each term has an h in it, so factor. And now it's time to divide by h. So how are we going to divide this thing by this expression by h? Well, notice all these labels, equation labels that are being printed here by Maple. They stand for the item, and you can use that equation label to reference the item. The only thing is you've got to do a Control L, L for label, to bring up this insert label tool. That's where you would put the number of the label. That you can divide by h. And if you hit the enter key, you'll see that Maple has divided that expression by h. Now, if you're working with pencil and paper, you would get this far. And at this point, to take the limit as h goes to 0, what would you do? Well, I know what I would do. I would just set h equal to 0 and see if anything bad happened. If nothing bad happens, then I've got the limit. So I'm going to evaluate at a point, let h be 0, and I've got my 9x squared minus 11. So here's an illustration of how one might use Maple to bring a student through the manipulations pertinent to differential calculus in a way that shows them how to proceed and does the arithmetic and the some of the algebra in a way that prevents mistakes, organizes the result, and lets the student see the outcome in a way that pencil and paper just doesn't quite do it. Not for me, anyway. Now, it turns out that when a student is learning this material, each different kind of function that they test or try this on requires different algebra. And I want to show you what I mean here. The approach, limit of the difference quotient, if you let Maple take the limit, that's fine. But if you want to take the limit from first principles, then each bit of algebra is different. So here I'm going to work with a square root function. So I want to define the function. I'll just quickly type f of x equals, I'll use a square root symbol that I got from the expression palette, and here it's in my favorites palette. I showed you how to get stuff into the favorites palette. And then I want to define this as a function, so assign function. Now, we've seen how to build the limit of the difference quotient, so I'm just going to drag this thing down, do a control equal, and we get the derivative of the square root. It's 1 over 2 root x. And then if we type f of x and differentiate that, we're going to get the same thing. So again, we did the same thing that we did above. If we write the difference quotient, so let me type h stroke f of x plus h minus f of x. And we look at this difference quotient and we say, okay, we have to let h go to 0. If we don't do something algebraically with this, the limit is going to be very difficult. You're going to get x minus x, root x minus root x, 0 on top and 0 on the bottom. You get 0 over 0, indeterminate form. You have to do something to take this limit. And what you do to take this limit is different from what you did to take the limit on the polynomial. What do? You rationalize the numerator. That's the secret. So that's really what the student is learning here, rationalize the numerator. But Maple does not have a rationalize the numerator command. It has a rationalize the denominator command. So why don't we just flip this upside down, invert it, reciprocal, rationalize that, then flip it back again. So 1 over that thing, well, I can use the equation label to reference it. There, I've put the difference of square roots in the denominator. I will rationalize the denominator. So there's a rationalize in here somewhere. There it is. Rationalize. Okay, now we have to flip that back again. So it's another 1 over, I'll use Control L5. So here is the expression that's equivalent to this, except that h equals 0. And if you let h go to 0, here you get 1 over 2 root x. Let's just do that. Evaluate at a point, let h be 0, and you get 1 over 2 root x. So again, Maple has implemented the steps. The student can see the pattern of what the steps are, and I think there's less likelihood that they will make an arithmetic or an algebraic mistake and get led astray and then look at the mess that they've got on their paper and say, I don't understand this. And one of the steps in mastering the techniques of differentiation is the notion of implicit differentiation. So let's take a look at what Maple has got to offer for this problem in implicit differentiation. So I have an equation that defines either x of y or y of x implicitly. I'm going to think in terms of y of x. And before I even begin any of the manipulations, I'd like to know what y of x looks like. Can I even visualize what function it is I'm taking the derivative of? So control drag, I'm going to need this several times. I think I'm going to actually copy this to the clipboard because I'm going to be using that several times. Okay, so I want to draw a graph. Context panel, plots. There's a 2D implicit plot option, variables in the order x, y. I'll pick that. So here is an ellipse. I think I would like to make that smaller. There isn't a whole lot of room on the screen. Okay, so it's an ellipse. But you can do more than just draw that ellipse. Let's solve explicitly for y. So solve, obtain solutions for y. So these are the analytic representations of the two branches of the function y of x that this implicit equation defines. All right. I want to draw those two branches. So I'm going to go back here to plots. And I think I'll just have Maple do a 2D plot. It's defaults the -10 to 10. I'm going to live with that for the moment. But you can see the two branches, one in red and one in blue. And so now the student has, I think, a better idea of what function the derivative is being taken of. It's either this one or that one. So the symbol y will point either to this expression or this expression. Okay, so let's now get the implicit derivative. Let's just have Maple tell us this is what the implicit derivative should be. Go to the context panel, differentiate implicitly, and a dialog comes up. Dependent variable. I want it to be y. Independent variable. Therefore, it will be x. Say OK, and there is what a pencil and paper manipulation is going to end up producing. That's what the implicit derivative looks like. Okay, now that we know what we're supposed to end up with, let's take a look at this task template. Now, what are task templates? Tools, tasks, browse, table of contents comes up, calculus, differential, derivatives, implicit differentiation. There are three categories one more complex than the other. We're looking at the simplest case. This is the task template. It can be inserted by clicking one of these two insert buttons. Default content means you get this extra verbiage. Minimal content means you get enough to make the thing work. And I've got that already embedded in my worksheet. Here's the path to it, the one we just followed. Insert the defining equation. Dependent variable, y. Independent variable, x. When we press this button, we get the implicit derivative that we just got from the context panel. But now we have the 4 steps of the algorithm, the first of which is the most important one in my mind, which is find where the hidden x's lurk. In other words, each y should explicitly show where the independent variable is. So y of x, y of x. And then, if you knew all the rules of differentiation perfectly, differentiate with respect to x. And that's what this button does. You differentiate with respect to x, but as students learn this material, they may have some qualms about products like x, y of x and y of x squared, where they don't see the terms, they just see the symbol. So we click this stepwise button and a tutor appears. This is one of the tutors. Yeah, I'll put that away for a second. Tools, tutors. More than 50 tutors, single variable calculus, differentiation methods tutor. That's the tutor that we're going to use. There's one like it for integration, and there's one like it for limits. It's a stepwise application of the rules of either differentiation, integration, or taking limits. All right, so let's look at this tutor. By going through this button, the function that we want to deal with is here, and it's up to us to select an appropriate rule to start with. If you pick a rule that doesn't make any sense, maybe we'll tell you, no, don't do that. And it tries to give you a hint. It says, notice the plus. If that doesn't make you realize that you need to press the sum button, you can ask Maple to give you help. So you press next step, and it says the sum rule has been applied. This is what happens when you apply the sum rule. Everything breaks up into pluses and minuses. This first term has a multiplicative 3, so there's this constant multiple rule. Now you can apply the power rule, and you get the 6x. These two terms have constant multiples. This term is the derivative of a constant. If we do that, we get rid of it. Derivative of constant 0. Now, right now what I'm going to do is I'm going to hit this constant multiple button twice, once for each of those two terms. So we've taken out the constant multiple here and the constant multiple here. There is this thing about understood rules. You get to a point where you say, well, I understand the need for the constant multiple. Don't remind me of that anymore. Just go past that step. I don't want to have to stop and worry about that. So you can select one of these rules, like the constant multiple rule. Then Maple will tell you, okay, fine, I'll do it for you. This term is a product, x, y of x. So you see what happens when you apply the product rule. You get two terms, first times the derivative of the second plus the second times the derivative of the first. All right, derivative of x with respect to x, Maple calls the identity rule. And we've taken care of the product, okay, because this is just y prime. This is the chain rule, so let's see what Maple does with the chain rule. It says right in here, it's derivative of underscore x0 squared, because the outside function is a squaring function, and there's no unique mathematical representation of that. So something squared, and you take the derivative with respect to that something. You evaluate with that something set equal to y of x, and you multiply by y prime. So this derivative yields to the power rule, and the derivative has been taken. That's how this is obtained. What's next? Isolate the derivative. So you solve for the derivative, and when you're working with a pencil and paper, when you get this far, you might as well change y of x back to y. Well, having the student go through these 4 steps of the algorithm through the tutor gives them some insight into what they're trying to do, and in fact, those steps can be implemented from first principles, and they would be applicable in more than just this simple case. So let's begin with the defining equation. Let's change y to y of x, so evaluate at a point and change y to y of x. We have to differentiate with respect to x. That's the next step. So differentiate with respect to x. And then we need to isolate the derivative. So if I select the derivative and go up here, I see I have an isolate option. So I select that. And Maple solves this equation for y prime. Now, as you move along through the course, after differentiation has been mastered, there's a whole bunch of applications of differentiation. So here's one. It's unconstrained optimization. Happens to be the minimum distance or point closest to a fixed point as you move along a graph. So here's the function. Here's the fixed point. And before I even get started, I'd like to make it clear to the student just what it is that they're trying to do. So here is an animation. This slider is controlling the x coordinate of that red dot. The red dot traverses the graph of the function. The distance between the black dot, which is the fixed point, and the red dot is calculated and displayed here. And here's the display of the x coordinate. And by manipulating the slider, you can look at the distance, and I think 1.62753 is the smallest I can get with this pixel arrangement. And you look and you sort of suspect that the green line between the fixed point and the point on the curve is orthogonal to the curve. So by playing with this, you begin to understand what it is that you're trying to do. Okay, now for the actual solution process. Let's first consider, I'm going to close this here. First consider the issue of the exponential e. And there's a note about that here. If you type the letter e, just even in math mode, that is not the exponential e. That's just the letter e. Happens to be typed in math mode, but it's not the exponential e. To get an exponential e, you got to do one of two things. One way is to use command completion. And command completion can be implemented most easily by pressing the escape key. When you press the escape key, you get a list of all of the things in Maple that start with e, the very first of which is the exponential e. If you make that selection, you have now the exponential e. Another way to get an exponential e is to use something from a palette. Now, I've got an exponential e in my favorites palette, and when you hover on it, it says exp of 1, telling you it's the exponential e. I think I got it from Common Symbols here. And then I put it into my favorites palette. So you have one of those two choices. So if you're going to work on this formula, you're going to have to realize that I typed this with just the letter E to make it look like it would look in a textbook. You notice when I put in the exponential E, it doesn't look like the E that you would get in a textbook. Okay, so first thing I want to do is I want to install the Student Calculus 1 package. Tools. Load package. Student Calculus 1. So I've loaded the package. Now I'm going to define this function. Drag it down. Do a control drag. And before I define the function, I want to change this E to an exponential E. And I just overwrite it by clicking on appropriate item there in my favorites palette. And now I can do an assigned function. So I'm ready to roll. Distance between a point and the function. So points use lists 1, 7, and lists are the square brackets. The other point is the point on the curve, so that's x, f of x. In the Student Calculus 1 package, which I will have here, Maple looks at what I've clicked on and says the only thing that makes sense to do to those two lists would be compute the distance. I want to make a function out of that. So I'm going to write d of x equals, I'm going to reference this expression by its equation label, Control L2. This is the rule. I'm going to assign function. Right there, assign function. I have now made this thing the function d of x. When you have an equation label and you're wondering, well, what does that equation label really point to? If you right-click on it and change label to label reference, in other words, that which the label is referencing, then Maple replaces the equation label with the item so you can see the mathematical statement, d of x is this stuff, and I've made a function out of it. Okay, I want to draw a graph, right? And you're going to want to minimize this thing, so why don't we just draw a graph and look and see, does it even have a minimum? Where would that minimum be? So d of x, press the enter key, so there's the rule, and now draw a graph. So I'm going to use the plot builder. So plots, down here you have this tool called the plot builder. And I'm drawing a 2D plot. The default is -10 to 10, and you have a hyperbolic function, exponential function. You get big numbers. So we have to change the plotting range. We don't want to go from -10, 0. And I think if we go to 4, that will be enough. So we have a curve which appears to have a minimum. Now Maple has altered the vertical scale range. It doesn't start at 0 and it goes way up high. So let's see if we can find a place where we can change the view. I would like to see from 0 to about 7 or 8. Now let's try 7. Alright, we can see there is a definite minimum somewhere between 2 and 3. And that's what we're trying to do. We're trying to get a graph to show us roughly where the minimum is. Next, we can minimize numerically. So if we do d of x and hit the enter key, go to the context panel, find optimization, and minimize. This be a local minimization, and we get a numeric minimization. So the x is between 2 and 3, 2.6 something, and the minimum value, this is the minimum value of the distance, Maple reports 1.627. first principles. Set d prime equal to 0, and you do exactly that. D prime. Now you can use an apostrophe. Here, this is what it looks like. I don't think that looks as nice as this prime symbol, which I have put in my favorites palette. I've got prime, double prime, triple prime. That comes out of the punctuation palette. There's prime, double, triple. There's even a quadruple prime, which I never use. So d prime of x equals 0. Maple does the differentiation, and we want to solve this thing. Now, there's no way you're going to get an analytic solution out of that. Hyperbolic sine, hyperbolic cosine, exponentials, you have to work numerically. So we're going to solve. We have to work numerically. If we say numerically solve, Maple will pick the initial point of the Newton iteration, which is going to take place, and it's going to end up at the wrong root. So let's tell Maple the initial point that we want the iteration to start from. I'll pick 3. And it ends up as 2.61, and if we look over here, 2.61, computed the appropriate point. If you want the actual distance, type d of, and this point has this x hat has an equation label, Control L7, Control equal, and you get your 1.627, blah blah blah. And if you want to know the y coordinate, it's f of Control L7, Control equal, and it's 6.7, and if you go back to the graph, not this graph, but back to the graph of the function, that 6.7 is up here somewhere. Well, after unconstrained optimization, course then looks at constrained optimization, and here's a problem in constrained optimization that I'll look at. It's pretty standard. Largest rectangle that can fit in the upper half of this ellipse, and all of the stuff about the sides of the rectangle being parallel to the coordinate axes, all of that stuff is part of the problem. Again, I'd like to start with a picture. So here's an animation that shows the upper half of the ellipse and a rectangle. Its rectangle is in red, and the animation is controlling the size of the rectangle. So as I move the slider, two things are happening. This is the x-coordinate. Right up here you have the x-coordinate of the right edge. And so this is the negative of that number. And this is the area of the red rectangle. So we would like to maximize the area. 746. See, I think 746 is the biggest that I can get using this pixel count. So again, here's an animation that illustrates what it is that you're trying to do. And this is how I like to start these various applied problems, so that it's not just abstract symbol pushing, that it's something you can tie to reality. Well, having drawn a picture, let's see if we can get at least a numeric solution so that we know what ballpark we're in. Does it match what we just saw in the visualization? So we want to make a sequence of the objective function. Now what is that? Well, from the picture, 2x space for multiplication y, that's the area of the rectangle, 2xy. Then we want to put the constraint equation, so I'm just going to drag this over. Constraint equation. And if we go to optimization here in the context panel and select maximize. We have an X and a Y and a maximum area, 7.74. I think we had 6 here. Okay, so ballpark estimate numerically obtained just to see if we're going in the right direction. Then finally, a solution from first principles. Now, in Calc 1, you can only work with one variable. So the objective function, 2xy, the y, well, or you could replace the x, but the y is going to have to be replaced with y of x. And to do that, let's grab this constraint equation and let's solve it explicitly for y. That's typically what you have to do. So context panel, solve, obtain solutions for y. Okay, the upper half is this positive square root. This is the upper half. So I want to make a function a of x equals 2x. Then I need this stuff. So put a space for multiply. I'll drag that stuff down. Then I want to assign function. If I type a prime of x and set that equal to 0, a prime of x, and set that equal to 0, I have the appropriate equation that determines x. Now, if you're working with a pencil and paper, you'd probably have to simplify this before you could make any real progress here. So let's do a simplify. There, simplify. Take the simplest simplify. And you can see from this expression what the answer is going to be. It's going to be either plus or minus the square root of 6 persist. Let's do the solve. Solve, simplest solve will work. It's plus or minus the square root of 6. Well, how big is the square root of 6? We can do that. We can select this second element, and I believe we approximate, how many digits you want? 10 digits. You get the numeric approximation of x, and sure, it agrees with the x we found up here, 2.449. 2.449. What is the y coordinate? Because it wants dimensions of the rectangle. Well, this is the appropriate expression for y. We drag that down. We want to evaluate that at x equals the square root of 6. So we could do that by evaluating at a point. Let's just put SQRT 6. I don't know how much simpler this would become. I don't know what simplify will do. Let's try it. Simplify. Oh, it pulls out the 9, which is 3. The square root of 9 is 3. And if you want to approximate that, I guess you could approximate that and get the height 1.58 for the height. Does that match anything we've done? Yeah, 1.58. There you go. Okay. So again, this is a cascading approach using Maple to get some insight. You draw a picture, you get some insight, you get a numeric solution, then you apply first principles. You let Maple do the heavy lifting, and you just guide Maple through the computations. You do a few of these and you begin to get the idea of this is how this stuff works. And I found that it made it much easier to get the abstractions across the students. After the constraint optimization, one of the groups of applications that shows up are related rate problems. And to my mind, related rate problems are nothing more than application of the chain rule. And that's really what's behind the related rate problem. But the students struggle with these problems because they haven't mastered the skills of problem solving by and large. I mean, you get a handful who do, but when students struggle with this stuff, they're struggling with problem interpretation and problem setup. Very little calculus is involved. It's supposed to be just an application, and these things take on a life of their own. So this is the classic sand pile problem. Sand pours from a hopper at a steady rate, forms a conical pile. Height is twice the radius of the base of the cone. Now a measurement is made. When the height of the pile is 20 feet, the radius of the base appears to be increasing at the rate of a foot every 2 minutes, or half a foot a minute. How fast is the sand pouring from the hopper? Well, steady rate, sand pouring from the hopper. Need a picture. This is a cross section through the axis of the cone. This is the height of the cone. This is the radius of the base. And there's a statement in here that says radius of the base appears to be increasing at a certain rate. And there's a statement over here, the height is twice the radius of the base. So h is 2r. This is r. So you begin with that. Then the next thing you need is the volume of a cone, 4/3 r cubed h. The height is 2r. And what do you know? You know r dot. You know the rate of change of r. It's a half at a particular moment. It is known at the moment when the height is 20 or when the radius is 10. Right? Height is 20, radius is 10. So all of this extraction from the words of the problem are what distinguishes the problem solver from the student who says, I can't work number 5. All right? What are we looking for? We're looking for v dot, dv dt. Here's the solution. How are we going to do this? Begin with writing the volume as a function of t. We need this expression. Now, h is 2r of t. So this is going to be an r of t. So we're going to have 2 pi over 3. 2 pi over 3. We need an r cubed, and it has to be explicitly made a function of t for Maple to understand what it is that we're doing. Okay, so there's an r squared. You pick up a 2r from the h, and now you have an expression in r of t. And we want to differentiate this with respect to t. So differentiate with respect to t. This is the unknown v dot, and we want to find out what v dot is worth when r is 10. So this r will become 10, and this r dot will become 1/2. One way to do the evaluation is to make use of this eval template. Okay, you'll find that up in the expression palette. It stands for eval, the eval function. So let's click on that. What are we evaluating? We're evaluating the stuff that has control label, equation label 2. And r of t is 10. R dot T is 1/2. That's V dot. Another application of derivatives in the Calc 1 course would be curvature of a plane curve. So let's tackle a curvature problem. Here is the formula for curvature. Notice that in modern books, modern calculus books, they take the absolute value of the second derivative in the numerator here. In older books, and I had a copy of Granville Smith Longley from 1927 or something like that, they did not take the absolute value. So y double prime, which is the concavity, could be positive or negative, and you got one more piece of information, and that piece of information was how was the shape of the curve buckled, up or down. But nowadays, curvature is taken as positive. And to make this a little bit more interesting, I'm going to take the curve to be an ellipse, and I'm going to ask where are the curvature's maximum and minimum. I'm going to begin with a graph of the ellipse. I'd like to see what it is I'm working on. Context panel, plots, 2D implicit plot using X and Y. Wow, look at this. This comes up, looks like a circle because constrained scaling has not been applied. Well, one way to apply constrained scaling would be to right-click on the graph and you would have constrained scaling. I think another way is right there in the context panel, there's a little checkbox for constrained scaling. All right, so now we have a graph of the ellipse. It would appear that the semi-major axis is 5, and the semi-minor axis is 2. We want to get y of x because this formula requires y of x. And we have two branches. There's an upper branch and a lower branch. I'm going to solve for the lower branch, and here's why. On the lower branch, the concavity is positive. So y double prime will be positive. So if I work with the lower branch, I don't have to worry about any absolute value because it will come out to be positive. Let's solve this thing for y and pick the appropriate branch. Context panel, solve, obtain solutions for y. The lower branch is this one. So I'm going to select elements, select element number 2. That's the lower branch. Now, I want to make that into a function g. G of x equals this stuff, and I will reference it by its equation label. Oop, I made a finger mistake here. Let's see what I did wrong. I think I see what I did. Let's try this. G of x equals, I think it was just a typing mistake, and then it was Control L, I needed 3, and that's what I want to make a function out of, so I assign function. Okay, so this is just because I'm looking at the keyboard, I'm not looking at the screen and checking what I'm typing. The curvature function that I've written here has no absolute values and is written in terms of g of x. I didn't want to muck up y of x because y of x already has a meaning. It has meaning for the ellipse. So by calling this branch g of x, I can use this formula. So what I'm going to do is I'm going to just pull this thing down here. Maple knows what g of x is. There's the curvature. But it certainly needs to be simplified. So I'm going to try context panel here and try simplify. I have lots of choices, and the one I want to pick is I want to tell Maple that x is small enough that 25 minus x squared doesn't go negative. If it goes negative, you got all kinds of problems with that square root. So assuming real range. And I get this dialog. And you see here I've pasted in what the dialog should look like when I'm done. Minus 5 to 5. But that would be a closed interval. I want this to be an open interval. I don't want x to actually hit 5. So now I have a much simpler form of that curvature, and I think I want to give that a name. I guess I'll give it the name kappa. So assign to a name, and I have to type in here kappa, K-A-P-P-A. Alright, so kappa now stands for this expression. And I was looking for a maximum and minimum. Well, before we go any further, let's go back to the graph and see where do you think the maximum and minimum would be. The maximum curvature appears to be at the endpoints here and here, and the minimum curvature appears to be down here where it's flattest. So the minimum curvature should turn out to be x equals 0. The maximum curvature should turn out to be where x equals either plus or minus 5. Let's draw a graph of the curvature. So there's the curvature. And let's do a graph. Plot. Just 2D graph. Now that's defaults minus 10 to 10, but Maple didn't find anything out here beyond 5, so it just draws this graph. Now I'm looking for a maximum and a minimum on this graph. Well, the minimum is obvious. At x equals 0, that's clearly where the minimum is, and that agrees with our intuition. Where's the other extreme point? The 5. The end point. As x approaches 5, curvature is going up here. Maximum curvature is up here at x equals 5 or minus 5. If you do this analytically by taking derivatives, so let's kappa, and you differentiate this thing. If I can control my fingers here, we have a differentiate with respect to x. If we set this equal to 0, obviously we're going to get x equals 0. You want to go through that step, you get x equals 0. That's this point down here. It's the only extreme point you find because the other extreme point is at an end point. So to get that, you would have to know it's the end point 5. But I'd like to see what the curvature is when x equals 0. So let's do a substitute into, and we're going to substitute x equals 0 into kappa. We'll see what the value is. Well, square root of 625, that's 25. So this could be simplified. So let's do a simplify here. Simplify. 2 over 25. For the maximum, you simply have to plug in x equals 5. So let's do evaluate at a point. X equals 5. And square root of 100. This can be simplified. So let's do a simplify. Where did that go? Simplify 5/4. So the minimum 2/5, maximum 5/4, consistent with our intuition by looking at the graph. And the implementation of this stepwise, pencil and paper wise, you'd have to get y, you'd have to get y prime, and you have to get y double prime.